A molecule will be polar if A, the bonds are polar. You have to have bonds that are polar, difference in electronegativities, and the molecule is not symmetric, and this is worth discussing. Now, first of all, we've been talking about bond polarity, and every time you have a delta chi, a change in electronegativity that's basically bigger than 0, all right, you're going to have a polar bond. However, you can have symmetric molecules where all of the polar molecules kind of cancel each other out. These are examples of molecules with a central atom, but everything around the outside is the same. So for example, on the linear example on the left, you'd have something like beryllium difluoride, beryllium in the middle, fluorine on the outside. Let's use that as an example. Beryllium is probably like me if I'm going to try and wrestle with someone like Arnold Schwarzenegger, who's one of my heroes, actually, just to be honest. But anyway, let's say that Schwarzenegger is one of the fluorines, all right? Well, Schwarzenegger, even as he's older, is like so tough in my mind. He would totally take me down, all right? It would be no problem. He could like pull on my hand and it would pull off. I think of Schwarzenegger as really cool, obviously. But anyway, I digress. The fluorine beryllium is also really polar. Beryllium's it's basically a metal. Fluorine's a super non-metal. Fluorine's pulling really hard. However, there's another fluorine pulling on the opposite side. So earlier I said how Schwarzenegger could pull my hand right off. It's probably true. Let's say Schwarzenegger had a twin, and his twin was just as strong as him. Either a clones, that would probably be a better way. So Schwarzenegger and his clone are pulling, but they're pulling on 180 degrees apart from each other. Their pull is going to cancel out. Now, in chemistry terms, the fluorine is pulling electron density towards itself big time compared to beryllium. But the pull to, say, the right side is canceled by the pull to the left side. So if you have a symmetric molecule, and these are all examples of symmetric ones, by the way, where everything around the central atom is the same, no lone pairs, no fluorine versus chlorine, I mean, everything is the same, those are going to be nonpolar. So BeF2 is nonpolar. Each F-Be bond, very, very polar, but they're 180 degrees from each other, so they cancel each other out, and they're all nonpolar. Boron trifluoride is an example of 3 around a central atom. It's nonpolar. The next one would be CF4 or CH4. Again, as long as everything is the same, then it's going to be nonpolar. An unofficial hint is that if you have to guess, and this is always dangerous to say, especially as an instructor who's supposed to know better than to tell you these things. However, if you have to guess polar, because there's a lot more polar things out there than there are nonpolar. But I'd like to show you the official rules for finding nonpolar and polar before you have to guess. Yeah. So let's compare carbon dioxide and water. Which one is polar? Okay, so first you got to draw out the Lewis structure, figure out the geometries, stuff like that. Well, carbon dioxide, carbon in the middle of 2 double bonded oxygens. We saw that had formal charges of 0. Water, on the other hand, has a tetrahedral electron pair geometry and a bent molecular geometry. Well, CO2, the carbon-oxygen bond, has a delta chi, which is pretty good. I think oxygen is 3.5, and I think carbon is like 2.5. So the difference between those, 3.5 minus 2.5, is 1. That's pretty polar. But they're 180 degrees from each other, so they cancel out. CO2 is nonpolar. It has polar bonds, but the molecule is nonpolar. Now, water, on the other hand, doesn't even have the symmetry thing going for it. Remember, water has 2 invisible lone pairs on it. It's tetrahedral. Those angles are 109 degrees. This isn't symmetric at all. The oxygen-hydrogen is polar. It's got lots of lone pairs. This has polar bonds, and it's a polar molecule because not everything is the same. Lone pairs are different than atoms. They are not the same. So as long as everything is different, you will have a polar molecule. All right, let's play the polar-nonpolar game now for these molecules. Boron trifluoride, Cl2CO, and NH3. These are all what they call AB3, where there's a central atom with 3 different atoms around the outside. So first thing, big surprise, draw a Lewis structure, figure out geometries, blah, blah, blah. Well, all of these have 3 atoms around a central atom. However, they're all quite different here, you can see. BF3 has very polar boron-fluorine bonds. I think the difference in electronegativity is like 2.0, which is pretty strong for electronegativity. However, the boron is symmetrically distributed with fluorines. There's no lone pairs, everything's trigonal planar, stuff like that. This molecule is nonpolar. So BF3 has very polar bonds. BF is very polar, but because it's symmetric, nonpolar molecule. You would not be able to measure a dipole moment around BF3. Now, Cl2CO, when you draw it out, has a carbon-oxygen double bond and 2 carbon-chlorine single bonds. And right away, you can see that everything around that carbon is not the same. You've got 2 Cls and a double bond O. That certainly are all different things. That's going to be polar. All right, you have a measurable polarity around that, which is kind of interesting. And ammonia, although it looks like it's a central atom with 3 atoms around it, there's that invisible lone pair. And again, that breaks the symmetry. So ammonia also is not a symmetric molecule. It's going to be polar. And you can see it's 1.47. The lone pairs on top of that nitrogen kind of give it an electron kick. So that's why it's a little stronger, I would argue, dipole than the Cl2CO. But kind of cool to think about. All you need to worry about is symmetric or non-symmetric for the molecular polarity. So BF3, symmetric molecule, just fluorine around boron, nonpolar. But the other one's definitely asymmetric, and that includes the lone pairs on ammonia, polar. Which of these molecules is polar? Okay, so the very best way to do this problem would be to draw out Lewis structures for the first 4 there and see if any of them are polar or if they're all nonpolar. Now, BCl3 is going to be very similar to BF3, a boron in the middle of 3 halogens. Instead of fluorine, it's chlorine. We saw that BF3 was nonpolar, BCl3 nonpolar as well. CO2, we also saw earlier, carbon in the middle of 2 double bond oxygens, 180 degrees from each other. CO2, symmetric, that's going to be nonpolar as well. Now, if you have 2 atoms, the same kind of atoms next to each other, those are automatically going to be nonpolar because 2 atoms are going to be pulling equally. On this particular molecule, I do recommend drawing out the Lewis structure. There's going to be a triple bond between the nitrogens, and each nitrogen has a lone pair. But again, nitrogen pulling on nitrogen, that's a symmetric fight, no big deal, nonpolar. The last one, though, Cl pulling on F, well, those are different kinds of atoms. That's going to be polar. No question. Cl pulling on F is not, there's no way that that's not going to be anything but polar. So D is definitely a polar molecule because you have different kinds of atoms. And please notice that Cl and F, it's not CIF. You can't have a CIF, but you can certainly have a CLF. If you're having difficulties recognizing Cl and Ci, you are always welcome to ask me, and I will tell you if it's Cl or Ci. But this one's definitely CLF, just letting you know, polar. This is a series of complexes that go from one symmetric molecule to another. So on the left-hand side, you have CH4, which is a carbon symmetric with hydrogen all the way around it. And you can see there's no dipole moment. It's nonpolar. On the far right, you have CCl4, which is also symmetric with only chlorines around the carbon. Again, that's nonpolar because everything around it is the same. So the left is nonpolar, the right is nonpolar, but everything in the middle is polar. That tetrahedron, if you add 1, 2, or 3 of different kinds of atoms, you're going to make it polar. Remember, it's a tetrahedron. It's not flat, all right? So you can't have like 2 atoms cancel each other or anything like that. Everything in the middle, quite polar. Only if it's symmetrically distributed by the same kind of atoms will it be nonpolar. So this is kind of a cool guide to see how this stuff all works out. all of these molecules are nonpolar due to their symmetry. All right, and that's another thing. If everything in the molecule is the same, then it's also going to be nonpolar. So notice like on ethene right there, you could have like a sheet of glass go through the middle, and it would be the same both left and right. That's going to be nonpolar. Same thing here for acetylene, like a thing of glass through there. You can draw lines of symmetry through all of these different things, and they're going to be the same. So we're going to build on our knowledge of polarity a lot more. Ferrocene, the lower middle one there, is an example of an organometallic compound. It's a compound with a metal, iron, connected to a carbon. We're going to see this is a way to represent different carbons. It's pretty cool. Ferrocene revolutionized organometallic chemistry in the 1950s or so. That's for a future discussion. But anyway, again, iron in the middle of those two things, that's nonpolar. Pretty cool how this stuff all works out. So polarity becomes pretty important when it comes to being a scientist.